In this chapter, we are going to talk about data normalization and why is it absolutely crucial to bother with data normalization and redundancy. Okay, so first of all, what is the motivation behind data normalization? Data normalization is the process of structuring a database in order to reduce data redundancy and improve data integrity. By the way, it was first proposed by E.F. Codd while constructing the relational database model back in the 1970s. So the aim of data normalization is first of all to minimize duplicate data. So of course there will be duplicate data in the database. Of course we just want to minimize the amount of duplicate data. Okay, then of course we would like to minimize data modification. So we may have to modify the same data multiple locations because of redundancy. We are going to take a look at a concrete example. And finally, we would like to simplify queries. So if the relationships between the given database tables are simple, then of course we can construct simple queries as well. So for example, if we have a database table like this, is it going to work fine? Of course, we can do something like this. So here we have the ID of the given students, the names, the ages, the name of the university, and the address of the university. We may pose the question that, okay, is it a clever way of storing data? Of course not. And you may pose the question why. And the reason is quite obvious. For example, if the address of the university has changed, then of course what do we have to do? We have to consider every single item in the database and we have to change the address if necessary. Or for example, what if the name of the university changes? Of course, again, we have to consider every single row on a one-by-one basis and we have to update the name of the university if necessary. So this is what we have been talking about, that we would like to minimize data modification. Sometimes we are not able to avoid duplicate data. For example, in this case, we are not able to avoid using the same university because of course multiple students may attend the same university. Okay, so this is a typical case of an unnecessary data repetition. This is called redundancy and it can dramatically increase the size of the database and it is hard to handle when dealing with update operations. What can be the solution? Of course, the solution is to create a new database table for the universities and we are going to have a distinct row as far as Harvard University is concerned with the given address and with a given primary key. And of course, as far as the student table is concerned, we can use foreign keys and we can reference the Harvard University with the valid address. And as you can see, we just have to store integers. There is no need to store chars or varchars as far as the name and the address are concerned. We just have to use integer representation as far as foreign keys are concerned. So this is a typical case how we can eliminate or at least mitigate data redundancy with the help of multiple database tables. And of course, a good question is how to achieve data normalization and how to reduce redundancy. There are several approaches. We are going to consider the three most crucial approaches: the first normal form, the second normal form, and the third normal form. So these are the topics we are going to talk about on a one-by-one basis in the coming lectures. Thanks for watching. In the previous lecture, we have been talking about that if we want to achieve data normalization and reduce redundancy, then we have to consider three steps. And in this lecture, we are going to focus on the first normal form. So database design is very similar to software architectural design. I'm not sure whether you are familiar with the solid principles or design patterns, but basically we have to ensure approximately the same principles. So we should design database tables that can be extended easily, and there are several criteria as far as the first normal form is concerned. First of all, every database table must contain atomic values. So for example, if we are considering the student ID, these are atomic values 1, 2, 3, 4. As far as student names are concerned, Kevin, Joe, Anna, and Adam, these are atomic values. What about the subjects? It is working fine for math, for physics, for literature, but what about the last row? It has math and physics. So as far as the last row is concerned in the subject column, it is not an atomic variable. It should be math or physics, but it is not a good practice as far as database design is concerned to use something like this, that the subject is math and physics. So what can be the solution? For example, we can create another database table for the subjects and we can reference the given subjects based on foreign keys. Okay, so this is the first criteria. Every database table must contain atomic values. Then every database table column must contain data of the same type. So here, for example, as far as the student IDs are concerned, these are all integers. As far as the names are concerned, these are all varchars or strings. So for example, when using date and date time, we have to make sure that we are going to use date and not date time or vice versa. Okay, so every database table column must contain data of the same type. Then every database table column must have a unique name. So here, for example, it is fine. We have a student ID, we have a student name, we have a student age, and we have a student related subject. All of the columns have different names, which is good because we are not going to be confused when dealing with the given columns. We know exactly that the ID is going to be this column, the name is going to be the student name, the age is going to be the age of the student, and so on. Okay, and finally, the order of the data is not important, and basically this is why it is advisable to use primary keys, because primary keys identify the items in the tables. So for example, if we consider these items, then it is absolutely crucial that the primary keys, or as far as this database table is concerned, the student IDs are going to identify a given row, and basically the order doesn't matter. If we have the student with primary key 1 as the last row of the database table, then it is going to work just fine. So the order of the data is absolutely not important. Usually we use primary keys in order to identify the given rows one by one. So that's all about the first normal form. It is quite simple. We just have to consider these statements. In the next lecture, we are going to talk about the second normal form. In this lecture, we are going to talk about the second normal form as far as database normalization is concerned. So what is the second normal form? First of all, we have to make sure that the first normal form related principles are not violated. And then we have to make sure that the given database table doesn't have any partial dependencies. So before talking about partial dependencies, let's talk about functional dependencies. So here, for example, when dealing with the student database table, when we have an ID, a name, and an age parameter, for example, the ID is going to be the primary key that's going to identify every single student uniquely. So we have the primary key of the student table. We can come to the conclusion that all other columns, so besides the primary key related ID column, such as the name of the student and the age of the student, these columns are depending on the primary key exclusively. And these kinds of dependencies are called functional dependencies, which is fine. So if a given database table has functional dependencies exclusively, it means that we have achieved data normalization, because every single column besides the primary key are depending on the primary key exclusively, which means that the primary key is indeed identify a given student. So the name of the student, of course, it has something to do with the student, and of course the age of the student has something to do with the student itself, because this is the age parameter for a given student. So the primary key or the ID is going to identify a given student, and all the columns such as name or age are depending on the primary key exclusively, and these dependencies are called functional dependencies. So let's consider what is a partial dependency. If we have a database table like this, when we have a student ID that's going to identify every single row in the database table, we have a university ID, we have a name of the given student, and we have the name of the given university the given student is attending. Is it a good database design? Of course not. So first of all, let's assume that we define the primary key based on multiple columns. So in this case, the primary key is the ID of the student and the university ID the given student is attending. So of course, it is possible to define a primary key like this. And if we consider other columns of the database table, then we can pose the question whether that given column is depending on both entities of the primary key or not. So for example, the name of the university depends just one of the components of the primary key. So despite the fact that the primary key is the ID and the university ID, for example, the name of the student depends on the ID of the student exclusively. It has nothing to do with the university. And this is the case with the university name. The university name has nothing to do with the student itself. It depends on the university ID as far as the primary key is concerned. And this is called partial dependency. It is an indicator that we should split the database table into multiple tables. So again, I don't want to repeat myself over and over again, but usually there's some confusion regarding partial dependencies. So partial dependencies have something to do with the primary key. So we have to consider the components of the primary key, in this case the ID and the university ID, and we have to consider other columns of the database table. And if a given column depends on just a single entity of the primary key, then this is called partial dependency, which means that the given column depends on just a single entity of the primary key. And of course, it is the same with university name. So the university name is depending on the university ID exclusively. And of course, it is quite straightforward in this case that the student should be separated from the university. So we could end up with something like this. We have a student with an ID, a student name, and the university is going to refer to a university in another database table. So that's all about the second normal form as far as eliminating partial dependencies are concerned. Thanks for watching. In this lecture, we are going to talk about the third normal form. So, first of all, we have to make sure that the second normal form related principles are not violated, and then we have to make sure that the given database table doesn't have any transitive dependencies. Okay, so what is a transitive dependency? So let's take a look at a concrete example. We have students with given primary key IDs, names, subjects, and teachers. So for example, Kevin with primary key 1 is a student that's learning Java programming language, and the teacher is Professor A. We have Anna that's learning C programming language from Professor B, and so on. The primary key is the ID of the student, so the primary key is the ID related column, and we have to check other columns. For example, let's consider the column teacher. A good question is whether teacher A has something to do with the student itself. And the answer is probably not. The student is totally independent from the teacher. Okay, they have something in common. To be precise, that the subject the given student is attending, so for example Java programming language, is presented by Professor A. So this is the first problem, but the second problem has something to do with transitive dependencies. So if we consider the teacher column and the subject column, then of course we can come to the conclusion that the teacher is not independent of the subject, because of course the Python programming language is presented by Professor D. So of course, if we know that we are attending the subject on Python programming, then it is guaranteed that it will be presented by Professor D. And vice versa, if we know that Professor D is specialized in Python programming languages, then if we know that the teacher is Professor D, then of course the conclusion is that the given student is learning Python programming language. So there is a dependency between two columns of the database table. That's not the primary key. So there's a fundamental difference between transitive dependency and partial dependency. As far as partial dependency is concerned, we are considering the primary key and another database table column. So for example, the university name depends on just one of the components of the primary key. So we have the primary key component and we have another database table column. This is when we are dealing with partial dependency. What about transitive dependency? If we are dealing with transitive dependency, then we are considering columns that have nothing to do with the primary key. The primary key is the ID column, and we are dealing with the subject and the teacher. So there is a relationship between the two columns, and it is called transitive dependency. Again, what is the solution? The solution is to separate the database tables, because the teacher shouldn't be a column within the student database table. There should be different database tables for the teacher, for the student, and maybe for the subject itself. Thanks for watching.